Well, good morning, good afternoon, or good evening, depending on what time of day it is that you're watching this video. In this video lesson, we're going to go over how to find the area between two curves. So we'll start out with a nice basic example here. We're going to find the area of the region bounded by the graphs of f of x is x squared plus 2x plus 1, and g of x is 2x plus 5. Okay, now, we know if we integrate a function, it finds the area in between the function and the x-axis. So if we want to find the area of a region bounded by two different graphs, we're going to integrate. But we got to figure out which graph is above the other graph and do the graph on top minus the graph on the bottom. The other really important things are where do the two graphs intersect? Where do the two functions intersect? That's our boundaries for the region. So the first thing we're going to want to do here is figure out where does x squared plus 2x plus 1, where does that equal 2x plus 5? Okay, so we'll go through and we'll solve this for x. So I'll subtract 2x from both sides, subtract 1 from both sides. I'll get x squared is 4, so I wind up getting x is plus or minus 2. Okay, so I know when I go to integrate now, I'm going to go from -2 to 2. Those are the boundaries, the lower and upper bound of my region. Now, if I picture this graph, what the graph looks like here, what we're doing, in a line 2x plus 5, that's just a line with a slope of 2 and a y-intercept of 5. It's going to do something like that. Now, I know the boundaries are plus or minus 2, so if I come over here to -2, 2 times -2 is -4, plus 5 would be 1. So at this point right here, that's when x is -2 and y is 1. Now if x was 2, I get 4 plus 5 is 9, so at 2, we're over here at 9. Then I know x squared plus 2x plus 1 is just a parabola that goes down and up. So that graph's going to do something like this, come through and go like that. So the region we're looking for here is this right here. This that I'm highlighting in yellow. That's the area we want. That's the region that's bounded by the two graphs. Okay. Now, if I integrate from -2 to 2 and integrate the linear function, the 2x plus 5. If I integrate that with respect to x, that's going to find all the area under this red line, all the way down to the x-axis. Right? That's going to find all this area. Okay, now we don't want this little bit below the blue line. We don't want this area included or this area included. So that area right there would be the integral from -2 to 2 of the parabola, which is x squared plus 2x plus 1. If I integrate this, I get this blue area. Right. If I integrate the 2x plus 5, I get this red area. That's what we're looking for, is this red area. So I want to subtract out the blue area. So I'll take the function on top minus the function on the bottom. Now, there's a property of logarithms that says if you get the integral from a to b of f of x minus integral from a to b of g of x, you can just integrate from a to b, which in this case is -2 to 2, the difference of the functions. So if I subtract these, 2x minus 2x are going to cancel, and then 5 minus 1 is going to give me 4, and then I'll have minus x squared. So I'm going to integrate 4 minus x squared. Okay, now another thing I'm noticing once I get to here, and I don't have to do this, but I think this helps, is that 4 minus x squared is an even function. In some lessons earlier, we learned that if you have an even function and you're going from the opposite of a to a, that you could just integrate from 0 to a, or in this case 0 to 2, and double your answer. Because even functions are symmetric about the y-axis. All right, so this will cut down on our work a little bit. Integrating this isn't going to be tough. It's only 2 terms, but if we had something that had a bunch of terms, that's a nice move. So now we're going to get 2 times. If I integrate this, I get 4x minus x cubed over 3, or 1/3 x cubed. Do it from 0 to 2. It's a definite integral. So I wind up with 2 times. Plug 2 in here. 4 times 2 is 8. Minus 1/3 times 2 cubed. Well, 2 cubed is 8 times 1/3 is 8/3. It's minus 8/3. And then I could think of 8 as 24 over 3. Minus 8 over 3 would give me 16 over 3. Times 2 would give me 32 over 3. So there's the area of the region bounded by those two functions. It's 32 over 3 square units. Square inches, meters, centimeters. We don't know what the dimensions are, so it's just square units. If we wanted to, we could write it as 10 and 2/3, but it's okay to leave it as an improper fraction. Okay, now just out of curiosity, I want to see how good my graph was here. So I'm going to pull up my calculator. All right, so I went into the y equals the graph of my calculator. I put x squared plus 2x plus 1 and the y sub 1, 2x plus 5 and the y sub 2. I'm going to graph it. Got a different window from what I've done before, so I'm going to hit viewing window, go to standard window, and graph this. And sure enough, that looks like our sketch. So we're trying to find this region here. So if this is with calculator, then I can go G-solve intersect. I see it goes from -2 to 2. Okay, then what I would do is I would go back to the main menu. I go to options, calculate, integrate, and I would do the 2x minus 5, or 2x plus 5, minus x squared plus 2x plus 1. Right, I would do it just like I had it originally. And I would do that from -2 to 2. We don't need to simplify it for the calculator. We just let the calculator do it like it's written. And look at that, 32 over 3. Now, if for some reason I had the functions backwards, let's say I didn't take a lot of time to figure out which function was above the other function. So I thought the parabola was on top. So I did x squared plus 2x plus 1, and then I subtracted the 2x plus 5. What do you think would happen? Well, if you're thinking we'd get the same answer, but just negative, then you're right. All right, so if we have our functions backwards, we're going to get the same answer. We're just going to get the opposite sign. And since we're trying to find area, we know area is always positive, so then we just make it positive. So we don't have to get really caught up on which function's above the other. It's nice, just for peace of mind, but if we wind up with a negative answer, then we just know we had our functions backwards. All right, let's try this one here. So we want the area of the region bounded by m of x, which is x times x squared minus 3x plus 3, and nx, which is x squared. All right, well, I'm going to go through just like I did in that last problem. First thing I'm going to do is distribute this through here. So this function m of x is going to be x cubed minus 3x squared plus 3x. Okay. To get an idea what this looks like and find the boundaries for my region, I'm going to figure out where these two functions are equal. So I'm going to take x cubed minus 3x squared plus 3x and set it equal to x squared. Then I'll subtract x squared from both sides, and I'll get x cubed minus 4x squared plus 3x is 0. I'll factor out an x, be left with x squared minus 4x plus 3 is 0. And then this factors to x minus 1 times x minus 3. So my zeros are 0, 1, and 3. So look at that. We've got two regions that are bounded here. First, it goes from 0 to 1, and then it goes from 1 to 3. Okay. So if I want to picture this graph, and I like to, if I'm doing it without a calculator, I like to picture the graph. And again, we could, right now, I could go ahead, and I know I'm going to integrate. I'm going to integrate from 0 to 1, one of these functions minus the other one with respect to x. And then I'm going to integrate from 1 to 3 one of the functions minus the other function with respect to x. Okay. If I don't take the time to figure out which one's above, then if I have them backwards, I'm just going to get a negative answer. But I always like to, just out of curiosity and for extra practice, I like to see what these look like. So x squared, I know, does something like this. X squared is just a parabola that goes like that. And then an x cubed, and I'll even do this here too. They intersect at 0, 1, and 3. So I know they intersect there. Let's say that's what x is 1, when that's x is 3. So I got a feeling this cubed one comes up here, goes from there, passes through there, and then turns around and does something like that. So I'm looking for this region right here and this region right here. And the important numbers here are right here, x equals 0. Right here, x equals 1. And right here, x equals 3. So I go from 0 to 1 and then 1 to 3. Now, from 0 to 1, the cubic function's on top. So I'm going to take the x cubed minus 3x squared plus 3x, so I'm going to subtract the x squared. But then from 1 to 3, the x squared's on top, so for this one I'll do x squared minus x cubed minus 3x squared plus 3x. Okay, now if for some reason my sketch is backwards, I'm going to get a negative answer for one of these. All right, or if I didn't take the time to do this, I just did them both with the cubic function minus the squared function, one of these would be negative. I'd get the right answer, just the opposite of the sign. All right, now we just get to work integrating here. So I would add like terms and simplify this expression. And I'll get x cubed minus 4x squared plus 3x. I'll integrate that with respect to x. And over here, I'll get the integral from 1 to 3. And then when I do this, I'll get a negative x cubed. Then x squared minus a negative 3x squared would be positive 4x squared. And then a negative 3x would be negative 3x. Okay, notice both of these are the same functions, just the signs have been changed. Hence, when we work it out, if we had them backwards, we get the opposite for the answer. So now when I integrate this, I'm going to get x to the fourth over 4, or 1/4 x to the fourth, minus 4x cubed over 3, 4/3 x cubed, plus 3x squared over 2, or 3/2 x squared. And I'll do that from 0 to 1. Okay. Now here it's going to be plus, and I'm going to get a negative. Integrate the x cubed, I get negative 1/4 x to the fourth. And then positive 4/3 x cubed. Now I just notice huge possible mistake here. This should be a minus right here. Right? Because when I'm doing this, or no, take it back. That's a plus. We wanted the minus here and here because we're taking the top function minus the bottom function. We've got two regions, so we got to find the area of this region and add it to the area of this region. So it wasn't a careless mistake. I wanted that to be plus. Then this is going to make the first term minus. This is going to be positive. Then I'm going to get minus 3/2 x squared. And now I'm going to do it from 1 to 3. So then we evaluate them. Plug 1 in there. I get 1/4 minus 4/3 plus 3/2. Plug in 0, we get 0. And then I'm going to get, if this is really plus this, so a positive and a negative makes a negative, positive, negative. So I didn't really need this plus in here. Plug 3 in here, I get 3 to the fourth, which is 81 over 4. So minus 81 over 4. Plug in here, I get 27 divided by 3 is 9 times 4 would be 36. And then minus 3 squared is 9 times 3 is 27 over 2. And then minus Plug 1 in there, I get negative 1/4 minus 4/3 minus 3/2 plus 4/3. So now I can go through, let's see, I'm going to need a common denominator. Might as well add everything up. Between 4, 3, and 2, common denominator would be 12. So I'll multiply this top and bottom by 3 and get 3 over 12. Minus, I'll multiply this by 4 and get 16 over 12. Multiply this by 6 and get 18 over 12. Multiply this by 3 and I'll get 243 over 12. Plus this 36, I'm not going to put it over 12. Then minus, if I multiply this by 6, I get 120 and 42, 162 over 12. This negative and this negative make a positive. And then multiply this by 3, get 3 over 12. Negative times a positive makes a negative. Multiply this by 4 and get 16 over 12. Negative and a negative makes a positive. Multiply this by 6 and get 18 over 12. So if I just work through now, 3 minus 16 is negative 13, plus 18 would be 5, minus 243 would be negative 238 over 12. I got that plus 36. Then over here, let's see, I'll ignore this. Well, no, I'll go ahead and do this. Negative 162 plus 3 would be negative 159. Minus 16 would be negative 175. Plus 18 would be 175 minus 18, 157. So minus 157 over 12. So let's see, negative 238 minus 157. I better do this over here. 238, 157. 15 carry 1 is 4 is 9. 395. I'm going to go ahead and do 36 times 12. I'm going to get 2 carry 1, 6, 7, 6, and 3. So 2, 13 carry 1. 432 minus 395. 432 minus 395. 12, it's going to be 7, it's going to be 37, so I'm wind up with 37 over 12. So 37 over 12 square units would be our area. And again, if it was with calculator, we could graph it, find the intersections, let the calculator do the integration. It'd be a lot quicker, more expedient way to do it. All right, so here's a nice area where we just had one region. Here's a nice example where you had two regions. Let's do a trig one. Let's find the area of the region bounded by j of theta is sine of 2 theta and k of theta is cosine of theta. And let's only look at it from 0 to pi. Right? Because these trig functions keep going forever. There's an infinite area of the region bounded. So let's just find the area bounded by these in between 0 and. All right, so without a calculator, first thing we want to do is find the boundaries of the region. So we're going to take sine of 2 theta and set it equal to cosine of theta. Okay, so double angle identities tell me sine of 2 theta is 2 sine of theta times cosine of theta. And I'm going to bring the cosine over. It's going to become negative cosine of theta, and that's going to equal 0. Once I have it equal to 0, I can solve by factoring. I'll factor out a cosine, and I'll be left with 2 sine of theta minus 1. So I need to figure out, where does cosine equal 0, or where does sine equal 1/2? Well, cosine equals theta at pi over 2. Right? Also at 3 pi over 2, but 3 pi over 2 is not in between 0 and pi. Now, sine equals 1/2 at pi over 6 and 5 pi over 6, which are both in between 0 and pi. So this is another one where there's 3 places, 3 independent variables where they're equal, so that tells me there's 2 regions. So first I'm going to want to integrate from the smaller boundary, the pi over 6, to the next one, which would be pi over 2, I'm going to do one of the functions minus the other function, integrate it with respect to theta, then add to that the integral from, then I'll go from pi over 2 to 5 pi over 6. And again, I'll do one of the functions minus the other function. Okay, now I could take some time and sketch this out, but maybe on this one I'll illustrate where it doesn't really matter if we do that. I like to do it so I can see it. I'm one of those people who likes to see the graph, but maybe that takes too much time, and we're taking a test. Time's valuable, right? Or we make a mistake sketching it. So let's go ahead and just do this. Let's assume the cosine is above the sine. Since cosine starts out at 1 and sine starts out at 0, it's 0, right? So let's do this. We'll do cosine of theta minus sine of 2 theta. Okay. Then, if we've got cosine above the sine, then the next time they should probably switch places, and the sine will be above the cosine. Or let's do this. Let's go ahead and do this. Let's just keep it the exact same way. Let's keep it cosine minus sine of 2 theta. Hey, I know one of these is backwards and one's the right way because the functions switch up. Okay, so one of these is going to give me a negative answer, but I just make it positive. So now I just go about integrating them, and the nice thing about leaving like this is the signs are the same. So to integrate cosine, I think to myself, what trig function's derivative is cosine? Derivative of sine is cosine, so that'd be sine of theta. And it's going to be minus, I have to integrate sine of 2 theta. And what I'm going to do here is I'm going to go, I'm going to go to the next page here, and let's say we were going to integrate the sine of some constant times theta with respect to theta. Right? In the other problem, we've got a 2 theta, but it could be a 3 theta, 4 theta, 5 theta, could be any constant. To do this, we would do a u substitution. I'd let u be k times theta, so then my du is going to be k d theta. Right? So I've got the sine of k theta, I've got d theta, I need k d theta, so I'd multiply this by k here and 1 over k over here. So now I'd have 1 over k, or 1 over some constant, times the integral of sine of k theta, which is now my u, and then the k d theta is my du. So when I integrate that, I get 1 over k times the derivative of cosine is negative sine, so the antiderivative of sine is negative cosine. So I get negative cosine of u plus some constant. So I'd wind up with negative 1 over a constant times the cosine of u, which was some constant times theta, plus another constant. Okay. So whenever we integrate the sine of a constant times theta, we're going to get negative 1 over the constant times the cosine of the constant times theta. Okay. So when I come back to this, that tells me, whoops, where did it go? Don't tell me I lost. That's funny. Hang on a second. I'm going to pause this and find out what happened. All right, here we go. That wasn't funny. I accidentally hit the delete page instead of add page and deleted this page, so I had to go back and get it. Okay. But now, based on what we just did, okay, if we integrate, this is negative sine of 2 theta, that should turn out to be negative 1 over 2 times the cosine of 2 theta. Right? And 2 negatives are going to make a positive here. So I get a positive 1/2 cosine of 2 theta. And then I'm doing that from pi over 6 to pi over 2. Then we're going to add to that. What's nice about keeping like this is this is going to be the same thing. It's going to be the sine of theta plus 1/2 the cosine of 2 theta. And then this one we do from pi over 2 to 5 pi over 6. Okay, so now it's just doing some trigonometry. Plug pi over 2 in there, sine of pi over 2 is 1, and it's plus 2 2 times pi over 2 would be pi. Cosine of pi is -1 times a half is -1/2. And then minus, put pi over 6 in there. Sine of pi over 6 is 1/2. All right, which it better be. That's how we got the pi over 6. We set sine of theta equal to 1/2. And then plus, put pi over 6 in here, multiply it by 2, we get pi over 3. Cosine of pi over 3 is 1/2 times 1/2 would give me 1/4. And then plus over here, put 5 pi over 6 in there, sine of 5 pi over 6 is 1/2. Then plus, put 5 pi over 6 in here, and we get 10 pi over 6, or 5 pi over 3. Cosine of 5 pi over 3 is -1/2. Times 1/2 would be -1/4. So this is going to be -1/4. And then it's going to be minus, plug pi over 2 in there, sine of pi over 2 is 1. And then this would be cosine of pi, which would be -1 times 1/2 would be -1/2. So now over here I get 1 minus 1/2 is 1/2. And then 1/2 plus 1/4 would be 2/4 plus 1/4 would be 3/4. I get 1/2 minus 3/4, which turns out to be -1/4. So that right there tells me I had my functions backwards right here. The sine of 2 theta was above the cosine, right? Because I shouldn't have got a negative answer. So what I'm going to do is take the absolute value of that, and I'm going to get 1/4. And I'm going to add to that. Over here, 2/4 minus 1/4 would be 1/4. And then 1 minus 1/2 is going to be 1/2. And then that's going to make it a -1/2. So we get 1/4 minus 1/2 would be 1/4 minus 2/4. We get another -1/4. But again, area can't be negative, so we take the absolute value and we get 1/4. And 1/4 plus 1/4 gives us 1/2. So the area of the region bounded by those curves is positive 1/2. And we didn't have to take the time to see which function was above the other function. And I'm sort of finding this interesting here. I was expecting this to turn out to be positive. And you know what I think? Look at this here. I got lucky here, but I made a careless mistake. Right here when I did 5 pi over 6, the sine of 5 pi over 6 was 1/2. Put it in here, 2 times 5 pi over 6 would be 10 pi over 6, or 5 pi over 3. That's 300 degrees. That's in the fourth quadrant. Cosine's positive. It would be positive 1/2 times 1/2 would have made this positive 1/4, which then would have made this 1/2 plus 1/4 would be 3/4, and then 3/4 minus 1/2 would be positive 1/4, and then 1/4 plus 1/4 is 1/2, right? So I knew this second one had to be positive if the first one turned out to be negative because we didn't reverse our functions. Right, and if I actually go and graph these two functions, right? If I graph sine of 2x and cosine of x, right, I'm going to go in here and change my window just to go from 0 to pi. And then I'm going to hit zoom auto just to get a better look at it. Okay, here's the sine of 2 theta. Here's where they intersect first at the pi over 6. Sine of 2 theta is above the cosine. That's why when we did this integral here, we got a negative. But then the cosine's above the sine. So when we did this, we should have got a positive answer. And we wind up with 1/2. Okay, so we did a nice one with one region. We did one that had two regions. We just did a trig one with two regions. What if we do one where we get a tangent line? That right there should be fun to do. So let's look at this one here. So we want to find the area of the region bounded by this function, 1 over x squared plus 1, and the line tangent to f of x at the point 1, 1/2. Now to find the area, I know we're going to integrate. And I'm already getting a whiff of this 1 over x squared plus 1. I don't know about anybody else, but that smells a little bit like arctangent to me. Now, let's do this one here. Let's sort of get a quick little sketch. 1 over x squared plus 1 should look something like this. It's just the bell curve. Okay, it probably looks a little bit better than that. I didn't get the greatest sketch, but something like that. Okay, as x gets bigger, positive or negative, this gets closer and closer to 0, so it approaches the x-axis. If I put 1 in, or 0 in for x, I get 1. So I know the highest this goes right here is the point 0, 1. Okay. Now we want to find the line tangent at the point 1, 1/2. So let's say that's maybe right here. There's the point 1, 1/2. We're going to have some tangent line that comes here that's going to cross the function over here, and we want to find the area in between the function and that tangent line. So to find the tangent line, we got to take the derivative of the function. So I think I would rewrite 1 over x squared plus 1 as x squared plus 1 to the negative 1 and use the chain rule instead of the quotient rule. Now, I like to do that whenever my function has a constant in the numerator. So this would be negative 1 times x squared plus 1 to the negative 2 times the derivative of x squared plus 1, which would be 2x. So my first derivative is going to be negative 2x over x squared plus 1 squared. Now my tangent line is going to be y minus 1/2 equals the slope times x minus 1. I just got to find the slope. So the first derivative tells me the slope. I want the slope when x is 1, so put 1 in there, I get negative 2 over 1 squared is 1, plus 1 is 2, squared I get 4. Negative 2 over 4 is negative 1/2. So the slope is negative 1/2. So y minus 1/2 is going to equal negative 1/2 x plus 1/2. Take this over here, it becomes positive 1/2. So the tangent line is negative 1/2 x plus 1. And that turns out really nice because the y-intercept of the tangent line is 1. So it goes right through this point, and our tangent line is going to do something like that. And then we're going to try to find this area right here. Okay, now if it hadn't turned out so nice, right? If it hadn't turned out that the tangent line went through the y-axis the same place our function did, then what we'd have to do is figure out where does our tangent line equal our function. Or in other words, where does negative 1/2 x plus 1 equal 1 over x squared plus 1? Okay, and to solve this, I would cross multiply over here. So I'd do x squared times negative 1/2 x would give me negative 1/2 x cubed. Then x squared times 1 would be x squared. Then I'd do 1 times negative 1/2 x plus 1, and that would equal 1. Then the 1's would cancel out. I'd factor out an x, let's say a negative 1/2 x from all these terms. And I'd be left with x squared minus 2x plus 1. And then this would factor to x minus 1 squared. So my zeros would be 0 and 1. Okay, this, we didn't have to go through this work. I did it just to show, because we already knew the point that it went through. We knew the boundaries were at 0 and 1. Okay. So now, if we want to find the area of this shaded region here, the region bounded by the tangent line and the function, then we're going to integrate from 0 to 1, and we're going to take the function that's on top, which is the 1 over x squared plus 1. So we're going to do 1 over x squared plus 1, and then we're going to subtract the tangent line, which is negative 1/2 x plus 1. We're going to integrate that with respect to x. So, again, we sniffed it out earlier. The antiderivative of 1 over x squared plus 1 is the arc tangent of x. And then this is going to be negative times a negative is going to give us positive 1/2 x. Integrate it, we get 1/2 x squared over 2. which would be 1/4 x squared. Then the negative times 1 would be -1. Integrate with respect to x, and we get negative x. And we do it from 0 to 1. So now if we plug 1 in there, we get the arctangent of 1, which means what angle has a tangent that equals 1? Well, tangent of 45 is 1, or in radians, pi/4. So the arctangent of 1 is pi/4. And it's plus, put 1 in here, we're going to get 1/4 minus 1. Then if we put 0 in there, arctangent of 0 is 0, because tangent of 0 is 0. This would be 0, this would be 0. That's nice. Those all turn out to be 0. So now I got pi/4, and then 1/4 minus 4/4 would be -3/4. So I get pi minus 3/4. That would be the area, the region bounded by 1/x² plus 1, and it's the line tangent at the point 1, 1/2. Now, again, if this was a with calculator question, then I would advise going to the calculator. Right, go in here, graph the function. Right, graph 1 divided by x² plus 1. I'm going to leave y sub 2 blank for right now. Okay, I'm going to graph this. I'm going to go back to a standard window, and I'll graph it. Okay, we're not seeing much. We don't need to go way up, so maybe I'll change the window. Only let y go up to 2, and maybe only go down to -1. Okay, so there I see it nicely. Now what's nice about these calculators is I can go into Sketch, F4, and I can sketch the tangent when x is 1. Okay, hit enter once, it doesn't really do anything, but you hit it again, look at that, it draws the tangent line. And it even tells me the equation of the tangent line is -0.5x plus 1, which confirms, right, what we got here, -1/2 x plus 1. Okay, I'm going to hit this, let's do zoom auto, and do this again. Sketch, tangent at 1. I'm not getting a nice picture. I wanted to see that we were under it. I could play around with this, but we don't need to. We know our tangent function now. So I'm going to come in here into y sub 2 and put in -0.5x plus 1. I'll graph that there, hit G-solve, intersect. One of the intersections when x is 0, and the other one is when x is 1. All right? So just like we did, we integrated from 0 to 1. Okay, then if I want to work it out on the calculator, I go back to the main menu. Again, I go to Options, Calculate, Integrate, and then I do the 1 divided by x² plus 1. And then I subtract the -0.5 x plus 1. Tell it to start at 0 and go to 1. Okay, and I know my calculator's in radian mode. I should have checked a long time ago. If I go setup, it's in radian. Right? That's what we want to be in. So if I graph that or I hit execute, get 0.0353. Let's compare that to pi minus 3 divided by 4, right? Which is what we got for the exact answer. Hit execute, guess what? That, my friends, is deja vu all over again. Okay, so you guys, this is a nice lesson here on finding the area of a region bounded by two curves. Always start off by finding the boundaries. Where are you going to start and stop in terms of x? And then it's nice to figure out which function's above the other one, but you don't have to do that. If you have them backwards, you'll get a negative answer. Just make it positive. Okay. If there's more than one region, like we had here, then you add the two regions together. Okay, I want to thank you for watching this video. Thank you for working hard. Always, whatever you do, try your best. Right now, you're investing in your future. It's going to pay off. So always, always, always remember, endeavor to persevere.